Welcome back. This is the third installment on the Bohr model. In order to understand this finishing video, you must have watched video number 1 on the Bohr model and video number 2. What you're looking at right now is the flame test that was demonstrated in video number 2. And I just want to call your attention to the red flame on the left. This is lithium when it's energized. The orange flame in the middle is sodium, and the sort of silver greenish flame on the right is barium. Okay, now just to reiterate what we did, I put salts of lithium, sodium, and barium in beakers. The beaker on the left had lithium, the beaker in the middle is sodium, and the beaker on the right is barium. Alcohol was added to each one, and the material or the alcohol was ignited, providing an energy source. And what we're seeing here is specific light waves in the visible range being emitted for each of the three elements, lithium, sodium, and barium. When energized, these three elements produce different color ranges. And what I want to talk about now is how Bohr used this information, the information that he got from experiments that have been done on all kinds of different elements that I spoke about specifically in video number 1. So what we're going to do now is go to the Bohr model. This schematic shows a qualitative representation of the Bohr hydrogen atom. And basically what it boils down to is that the electrons in an atom have specific energy levels where they can exist. They cannot exist between levels, only in the levels themselves. We call the energy levels n sub-levels. N equal 1 is the energy level that's closest to the hydrogen proton, and therefore is the lowest energy. We call energy level 1, n equal 1, the ground state, because when the electron is in n1, the hydrogen atom is in its lowest potential energy, because the electron is as close to the neutralizing effect of the proton as possible. So for hydrogen, the ground state is n equal 1. Subsequent energy levels are higher energy because the electron is being shifted further and further away from the proton. So the idea is that the electrons in any given atom can have different energies, but these are specific energies, and the energy shells are unique to a particular atom. So in order to shift the electron from n1 into n2, you have to put in exactly the energy difference between these two energy levels. And if you do that, then the electron in hydrogen can be shifted into energy level 2. When the electron reaches energy level 2, it's in an excited state and doesn't remain there, tumbles back down to n equal 1. And when it does that, its energy has to be given off, and the energy is given off as light. And as we saw in the experiment, the light given off is a specific wavelength. The energy of the electron when it's shifted from n1 to n2 is a specific amount of energy that has to be absorbed by the atom. When the electron tumbles back down, that exact amount of energy is given off as light. And since the energy being released is specific, the wavelength of light is specific. So the take-home message from the Bohr model is that electrons have specific energy levels that they exist in. We call these energy levels n sub-levels. The n sub-levels start at n equal 1 and have an increase in whole numbers. In the periodic table, the total energy levels is going to be around 7 energy levels.